In this analysis, we're going to look at an excimer laser. This is a pretty popular laser in research, particularly in chemistry, and it's because you can get different UV wavelengths out of this by changing the gas mix. And these UV wavelengths, having high energy photons, can break molecular bonds, and so it's pretty popular use in chemistry. Also, another piece of the research end of this is the fact that it can be used as the excitation mechanism or pump source to a dye laser, and the fact that you can change the wavelength makes it nice in pumping different dyes. Okay, so the excimer is, the name came about because it is an excited dimer molecule. Dimer being di meaning two, mer meaning two. Apart. So it's a two-part molecule. And an excimer molecule, what happens, this molecule only exists in an excited state, and once it's released its energy, it falls apart again. Okay, so that's the term excimer comes from excited dimer. All right, so our first look at this is going to be 248 nanometers. This wavelength is a pretty nice wavelength to use if we're processing materials, say cutting non-metal materials. This is a wavelength that is used, for example, in cutting holes in catheters, also processing kapton in the electronic industry, and that's because this laser uses an ablation process, so there's very little residual heating, and there's no cleaning up to do after processing those materials. So instead of using a heating process where we move from a liquid to a vapor state, it's a much cleaner process for cutting those materials. This laser is a little more to deal with in terms of the gas mixes and keeping it aligned and keeping it running. Nowadays, most people, if they need that UV wavelength around 248 to process materials, they have gone to a solid state laser, a YAG, and by pumping crystals and looking at the third and fourth harmonic, we can generate 355 nanometers and 266 nanometers in a much easier way with a solid state laser, and easier to maintain and much more stable in its running. So we've started going more towards solid state, but there are a lot of these lasers out there. So 248, a nice wavelength to process certain materials with. We have a repetitive pulse unit. The average power is 20 watts. We have a 25 nanosecond pulse duration. 50 hertz is the repetition rate. The ANSI default exposure duration is 100 seconds. And we're looking at a 1/E rectangular top hat for our spatial profile here. Now, the reason we're running 1/E instead of 1/E squared, it was to make a point that when you're dealing with a top hat beam, there's no difference between the 1/E and 1/E squared diameter. Okay, so it makes no difference. Here, we can take a look at that. Just watch the NOHD right here. It's 1640 meters. We will switch to 1/E squared, and you'll notice there is no difference in any of the outputs. So no difference in the diameter for a top hat beam when you're looking at 1/E or 1/E squared. It doesn't matter which one it is. But because we have a rectangular beam, we have a major and minor axis. The major axis beam diameter is 25 millimeters. The divergence is 5 milliradians. The minor axis, we have a 10 millimeter beam diameter and a divergence of 2 milliradians. We're going to look at our observer range at 1 meter here, selecting something different than the half a meter. And then we can take a look at the major and minor diameter. Here's the OD at observer range, worst case OD. And of course, we're going to look at our transmission through the limiting aperture. Our limiting aperture for both the eye and the skin is 3.5 millimeters. We have a transmission through the limiting aperture of 3.7%, so that's the difference between the OD at observer range and the worst case OD. I wonder how much power that is. 740 milliwatts is all that's passing through the limiting aperture. Okay. All right. So that takes care of the OD. Let's look at the NOHD. It is 1,640 meters. Well, we can see that the eye and skin limiting aperture are the same. The eye and skin, or ocular MPE and skin MPE, are the same. So we probably could come up with a pretty good guess that the NSHD will be the same as the NOHD, and that is the case here. All right. Notice how restrictive these MPEs are. These are really restrictive. Let's go take a look before we talk about this time skin MPE. Let's go take a look at our Rule 1 and Rule 2. Notice that even though this is a 25 nanosecond pulse, okay, at a low repetition rate, it is Rule 2, the average power MPE rule, that is dominating here. It's much more restrictive than the Rule 1, and that's because, remember, in this wavelength range we have both thermal and photochemical MPE we're looking at, and it's the photochemical MPE that's driving this analysis. And the photochemical is, we see the photochemical when we start getting into longer exposure durations, and so it makes this analysis much more, I should say the MPE is much more restrictive because we've moved into the photochemical domain because of the length of the exposure duration. The Rule 1 MPE is simply a thermal MPE. There's no photochemical involved in it because the time is too short. We need those longer times, at least greater than 10 seconds to move into the photochemical, being the photochemical MPE being the more restrictive. So clearly that's the case here, and that's what's happening, why we have such restrictive MPEs here. Let's look at this times skin MPE. So that's only about 250,000 times, the irradiance of this laser is only about 250,000 times greater than the skin MPE. I'm going to guess that this might be a skin hazard. Again, it's that photochemical MPE. You do not want to be exposed to this, because if it can break molecular bonds in materials, understand that it's doing the same thing in your biological tissue. And this is why when somebody's working in these wavelengths, we cover them up. Any exposed skin is covered, and instead of eyewear, you're wearing a full face polycarbonate face shield. And give you an example. We were involved in an audit with a company that had one of these lasers cutting holes in catheters. That laser had to be aligned, or tweaked up as we say, once or twice a day. We were talking to the engineer who was responsible for keeping that laser tuned each day. We were visiting the company. The company, it was outside Salt Lake City. This was in the winter. When I first looked at the engineer, I thought, oh, probably a skier. You know, he kind of had the raccoon eyes, and what I assumed was a sunburn on his face and on his hands is when I first noticed it. I wonder, maybe he was working outside, didn't have gloves. I didn't know. But as we got to talking, we realized that, he tunes this thing up every day, and it takes him, 10, 15 minutes to do this. All right. And so I directly asked, are you out, is the what appears to be a sunburn from you being outside, in the winter, skiing or something? No. Turns out it's coming from the UV laser. So immediately we started having a talk with, we've got to get you all completely covered up. You can't do this anymore the way you're doing it by just wearing the eyewear. We've got to cover up all your skin. Totally unaware of how dangerous this laser was. We suggested that he immediately make an appointment with his dermatologist, because he's going to have some skin issues. He'd been doing this for a couple of years, and so knew he's going to have skin damage, and it's going to start showing up in a few years, and he's going to need to address this immediately. And there is a topical drug that is used, cream fluorouracil, which is a topical chemotherapy drug, really. But what it will do is, if you apply it, it only targets damaged skin cells and begins pulling them up to the surface and sloughing them off. Okay, and so probably dermatologists would begin suggesting that they look at something like that to help him. Anyway, just wanted to point that out. So yeah, this is a real skin hazard. Okay, let's look at the diffuse reflection. The spectral reflectivity we're going to use is 100%. Viewing angle 0, worst case. Beam on target, doesn't matter, big, small, doesn't matter. We don't have a source type here. This is outside the retinal hazard region. Same MPEs for the eye and skin for the diffuse reflection as for the interbeams, and that's because it's running off the same exposure duration. The NHC for, in this particular situation, is 2.92 meters, so it's got a large diffuse NHC. The OD at the observer, standing at 1 meter away, is about 0.9, or really, close enough to 1 OD to call it that. And of course, the skin NHC and MPE are the same as the ocular. Time skin MPE is 8.53 for 100 for this particular analysis, and looking at 100-second exposure duration, it gives us this time based on the MPE, comparing it to the irradiance of the laser from a diffuse reflection, 8.53. I knew I'd finally get through that. So is this a diffuse skin hazard? Yes, it is. Okay. So yeah, there's just no way around dealing with the UV laser other than you've got to cover up. And so as the LSO, you're going to make sure anybody working with these UV wavelengths, we get all exposed skin covered up, whether you're worried about an intrabeam or not. If you're just worried about scatter reflection, yeah, this is a what I consider a dangerous laser to work with. All right. I think we've got, let's go down and take a look at laser calculated values, because it is something I do want to point out. You have a pretty significant single pulse here. Look at the peak power, 16 megawatts of peak power in that pulse. Now it is in a big beam, okay? So, that's one of the reasons that, it is in the big beam. So, you won't get the vaporization if you get hit with this if it was in something smaller. But you would certainly know you were popped with this, just a one pulse from it. And that's, look at the 25 nanoseconds, you have 400 millijoules in that pulse. Yeah, it's 20 watts, but you're only running 50 hertz. In order to get 20 watts only running 50 hertz, you're going to have a lot of energy in that pulse. Right? And then again, you can take a look at the duty cycle. Extremely low duty cycle. There are only 50 pulses within a second, and they're only 25 nanoseconds. So your on time isn't much compared to your off time, and that's reflected in a low duty cycle percentage. All right. So as I mentioned, we can change the gas mix, and we can get a different wavelength out of this thing, right? So let's go to KRF, the krypton fluoride. I'm sorry, this was a krypton fluoride, the 248. We're going to go to xenon chloride, and that's 308. This wavelength, successive day exposure, yeah. 308, when the laser is running 308, it has a nickname. It's called the cataract maker, and that's because of the perfect blend of transmission through your cornea and through the liquid between the cornea and the eye, right? And absorption in the lens of your eye, so that this wavelength attacks your lens beautifully. Yes, and it's called the cataract maker. If somebody works with this wavelength often, and they're not wearing eyewear, they will develop cataracts at a very early age. Okay. Now, if you look into section 8.2, ocular exposures, and you go down a little bit into that section, I think it's 8.2.3.1, somewhere around in there, you're going to see where they talk about UV exposures, And if you have multiple exposures within a 24-hour period, those are additive, and we call it successive day exposure. Okay, or at least that's sort of the term that we use in the software. And if you suspect that this is going to be the case, then you would answer yes to this. And what happens is the MPE is reduced by a factor of 2.5. So when I say yes to this, watch this MPE right here, and you're going to see it gets reduced right there. All right. So we've answered yes to successive day exposure. If you're not sure about the user, and the user says, well, sometimes we use it, maybe we use it just, 1 day a week, but then sometimes we use it, on 2 days of the week, successive days, then answer yes to that, and we'll just be a little more conservative on the result. All right. Now, something I need to point out here: when you change the wavelength, this default over here gets set. The exposure duration for the diffuse reflection gets triggered to go back to the default of 600 seconds. So let me set this back to 100. Okay, and what we can see is from the results of the OD and NOHD that this isn't quite as hazardous of a wavelength. Of course, that's because the MPE isn't as restrictive, and we'll notice that the times skin MPE isn't as high as with the 248. This is only 47,000 times above the irradiance of the laser is only 47,000 times above the skin MPE. So again, yes, still a real skin hazard. Yes, still a real hazard, but not as hazardous as 248, and that's because 248 is a higher energy photon. Okay, and based on how the absorption takes place and where what is absorbing, and in this case in 248 it's water, so it's happening right at the surface. 308 you're getting some penetration, so you have a larger volume of tissue dealing with the exposure. So we would expect 308 not to be quite as hazardous as 248, and in fact it's not. Now, whereas with the 248 the NOHD and SHD were the same, they are not in this case, and that's because the two MPEs are not the same. Okay? All right, so we have another wavelength that we wanted to look at. That was 351. That's xenon fluoride. I have a habit of sometimes saying xenine. I don't know why. Xenon fluoride. That's 351, and it's going to ask us again about successive day. Okay. Now notice what the MPE is here, and what you're going to see is that because we were looking at a wavelength and we'd already set successive day, if we answer yes again, you won't see a change in this because it's sort of automatically set up to go with, well, it's successive day. Okay. Only if I click no do you see what the real MPE would be without successive day, and it's the same as the skin, 110 milliwatts per square centimeter. So let's trigger that again by going 351. Let's trigger this again by going 351, not 315. Okay, there we go. We'll say successive day, and you'll see that it goes back to the 4 milliwatts per square centimeter. Again, 351, not quite as bad as 308, and certainly not as hazardous as 348. The NOHD is only 223 meters. For the skin, it's 141 meters. Let's take a look at the times skin MPE. Oh, good. This is, it's only 1,870 times above the skin MPE, the irradiance of the laser. So is this a hazard to the skin? Absolutely. Let's set this back to 100, and you can go ahead and take a look at everything through here and see that, yeah, as we move, make this wavelength longer, and based on what's doing the absorbing, or how much we're able to transmit through more tissue, so we're more volume is dealing with the absorbed energy, the less hazardous the wavelength is as it gets longer, and that's sort of what we're seeing here. Okay, so Let's see, I guess maybe the only other thing we could briefly look at is if I needed a barrier for this, and I know that maybe I have this Excimer and they run all through wavelengths. What I'm going to do is go back to 248. Notice that nothing changes here, and that's because it's really working off the power. This has nothing to do with biological tissue when we're looking at the irradiance in the beam itself. Okay, and I just wanted to point that out. So whether we're at 248 or we're at 308 or we're at 351, this never changes. Okay, so if I'm looking at a barrier, let's say my barrier is going to be 2 meters out, that's where I'll take a look here. Okay, I'll need a barrier that can withstand at least 6.9 watts per square centimeter, and then of course we will have a radiant exposure component to that too we want to look at, and it is 0.138 joules per square centimeter. I think that about does it for the discussion on this laser. So that's about it.